true one-dimensional electrons observed in phosphorus atomic chains. For decades, physicists have pursued a fundamental question: what truly happens when electrons are confined to a single spatial dimension? Now, researchers have experimentally confirmed that atomically thin phosphorus chains can host genuinely one-dimensional electronic behavior, a state long predicted but difficult to isolate in real materials. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Using high-precision surface science techniques at BESSY 2, the team studied short phosphorus chains that self-assemble on a silver substrate. Although these chains appear structurally one-dimensional, confirming that their electrons are also confined to one dimension is far more challenging. Neighboring chains can interact laterally, potentially restoring higher-dimensional electronic behavior. By carefully separating signals from chains oriented in 3 different directions, offset by 120 degrees, the researchers demonstrated that each chain independently supports a strictly 1D electronic structure. In other words, the electrons move along the chain and only along the chain. From 2 dimensions to 1. Most crystalline solids are 3-dimensional, with atoms bonded in all directions. The discovery of 2-dimensional materials like graphene showed that restricting atomic bonding to a plane can generate unusual electronic and optical properties. The next frontier is even more extreme confinement, reducing dimensionality from 2D to 1D. Theory predicts that 1D systems should exhibit dramatically altered electronic behavior, including enhanced correlation effects and unconventional transport phenomena. However, realizing a true 1D electron system without interference from neighboring structures has proven experimentally elusive. Phosphorus offers a unique platform. Under controlled deposition conditions, phosphorus atoms arrange themselves into short, straight chains on silver. While structurally promising, the key question remained: are the electrons truly confined, or do interchain interactions blur the dimensional boundary? Seeing one dimension directly. To answer this, the team combined cryogenic scanning tunneling microscopy (STM) with high-resolution angle-resolved photoelectron spectroscopy (ARPES). STM images revealed well-ordered phosphorus chains forming in 3 distinct crystallographic orientations. ARPES measurements then mapped the electronic band structure with exceptional clarity. By disentangling the overlapping signals from differently oriented chain domains, the researchers isolated the electronic signature of individual chains. The result was unambiguous. The electronic dispersion occurs along a single spatial direction, confirming authentic one-dimensional electronic behavior. Even more intriguing, standing electron waves were observed between chains, direct evidence of quantum confinement at the atomic scale. A density-driven phase transition. The study goes beyond confirming 1D behavior. Density functional theory calculations indicate that the electronic character of these chains depends critically on how closely they are packed. When chains are well separated, the system behaves as a semiconductor. However, as interchain spacing decreases, lateral interactions strengthen. At sufficiently high density, calculations predict a phase transition. The system would become metallic. In practical terms, simply adjusting chain density could tune the material from insulating to conducting without altering its chemical composition. Such controllable phase transitions are highly attractive for nanoscale electronics. Entering uncharted territory. This work opens a new experimental landscape. True one-dimensional electron systems are rare and theoretically rich, often associated with exotic quantum phenomena not possible in higher dimensions. By demonstrating controllable, self-assembled 1D electron confinement in phosphorus chains, researchers have created a clean platform for exploring these effects and potentially engineering new electronic phases by design. What other unexpected behaviors emerge when electrons are forced to live on a line? The answer may redefine how we think about dimensionality in quantum